All right, we are doing the first day titrations for babies. All right, number one, what's the whole point of performing a titration? The whole point is to solve a mystery or to calculate the molarity of a mystery acid or base. Okay, and it could be something like the amount of acid in a food, like vinegar, or it could be the amount of acid in something from a human, like urine. Label the equipment used when you're performing a titration. We've got an Erlenmeyer flask. We've got a burette. And remember, those are weird. They read from 0 to 50. Depending on the size, it could be different, but the top is 0. And the indicator that we are going to be using is phenolphthalein. There are other indicators that you can use, but phenolphthalein is a really good one because it turns bright pink as soon as it's basic. Alright, so let's take a look at these solutions. This first solution, I'm just going to look at it as far as kind of what's winning. There's a tie, there's a tie, there's a tie, and there's 2 hydroxide molecules, so that means this is a base. Let's check out this one. We've got HOH, HOH, HOH. This one is neutral. The number of hydroxide ions is equal to the number of hydrogen ions. And this last one, those match up. We've got extra hydrogen ions. That means this is an acid. So, which of these solutions, A, B, or C, would have a pH of 7? That would be B. Which one would have a pH less than 7? That would be the acid, letter C. And which one greater than 7? Oops, that would be A, the base. I was writing B for base. Sorry. Which one could be a soapy solution? That would be the basic solution. Which one would taste sour? That would be C, an acid. Which one would be slippery? That would be A, the base. Which one could be Diet Coke? Diet Coke is acidic, so that would be C. Using the picture from number 3, letter B, draw a new beaker showing what it would look like if a single molecule of Na was added to it. NaOH, sorry. So we've got H plus, OH minus, H plus, OH minus, OH minus, H plus, and then one more hydroxide ion enters. We could also draw the sodium entering, Na+, really a non-factor in acidity, but it's still there. So now we've got this extra OH, so the entire thing went from neutral to being basic. If phenolphthalein was added to beaker 3B, what color would it be before adding the NaOH? It would be clear, and then after it would be pink. Once the NaOH is added, the pH goes from being neutral to basic. Complete and balance this neutralization reaction. So it's a double displacement reaction. First 2 things swap places, so we're left with LiBr and H2O. And we're balanced. Imagine this. Stupid Mrs. Baker left out some HBr without a label on it. To save her from getting fired, you decide to secretly stay after school and perform a titration to figure out the concentration of HBr, add a label to it, and save the day. You had to add 5,000 milliliters of a 1 molar LiOH solution to 2,500 milliliters of HBr. Step 1. Write out the formula, yes again, and write down the numbers underneath, just like we learned in class today. Okay? So under the acid, I know that this is the mystery. We don't know the concentration. We know that we had the solution was 2.5 liters. Remember, you always want to change milliliters to liters, so you divide by 1,000. The base is a 1 molar solution and we needed to add 5 liters in order to neutralize this acid. So molarity times liters, we've got 5 moles of LiOH that we needed to add to neutralize that acid. Let's check out the ratio. The numbers out front of the balanced equation. For every 1 mole's worth of LiOH, you need 1 mole's worth of HBr to neutralize them. So there must have been 5 moles of HBr in that solution. And now let's figure out the concentration of it. Divide by the 2.5 liters. 5 divided by 2.5 comes out to be a 2 molar solution of HBr. So now we can put a label on it and I won't get fired. Let's put a picture at the molecular level with all of this, with what's going on. I'm going to take a second and actually just create some more space for myself and go on to the next page so I have lots of room to draw this. So we've got the base in a burette. Okay, there's a blown up burette. Here is my flask. In my flask, it's 2.5 liters worth of hydrogen ions, and we know from the answer that it's that there are 5 moles worth, so I'm just going to draw 5 H pluses in here, and we're adding some base. So we don't know how much base we're going to add, but this burette is filled with a whole bunch of hydroxide ions. Okay, so I could draw more, just smashing as many as I can fit. Alright, so you start adding drop by drop to perform the titration. Okay? Sorry, my cat's being loud. Alright, so as you're adding this to it, every H that you're adding, or every OH, sorry, is making water molecules. So it's neutralizing this. So that's after you added 1 hydroxide. So you've got a water molecule and you've got these 4 other hydrogen, 4 moles worth of hydrogen atoms. So you're still adding, and the whole time up here you're actually measuring how much base you're adding. Okay, and the amount of base is 1 mole per liter. So like each of these hydroxide ions represents 1 mole per liter. Okay, so you continue to add, drop, drop, drop. Here's another OH, another OH, another OH, another OH, and finally you get to that point where there's 1 extra hydroxide ion in there and it turns the whole thing pink. And you stop at that point and you figure out how much did you have to add. Well, according to this, you needed to add 5 liters of that 1 mole per liter solution. So you had to add 5 moles. So OH, 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 well actually 6 technically, because it wouldn't turn pink until it went over, but let's say it did turn pink right at that exact moment, because it's really not another mole's worth that you're adding, it's just a tiny little bit more. Okay, so anyways, you do your calculation based on how much base you needed to add, and then you still need that original amount of solution to do the calculation of what the molarity of the acid was. So it was 5 moles of hydrogen bromide or hydrobromic acid in 2.5 liters, so that's why we came up with the molarity of 2. So hopefully putting it with a picture helps a little bit. And again, the more titrations that you do, it's going to really help paint a picture.